A large vat is used to mix and dilute the dye used in making clothing. The vat begins full with 20 kilograms of the dye dissolved in 50 liters of water. This is too concentrated, so pure water is pumped into the vat at 16 liters per minute. The liquid is kept well mixed in the vat, and the resulting solution is pumped out at 16 liters per minute. Determine a function representing the mass of dye still present in the vat as a function of time in minutes. Okay, so what are we talking about? We want to talk about the mass of the dye that is left, still dissolved in the vat at t minutes. Okay. We're going to set up a differential equation for this. So we're going to want to talk about some of the derivatives of the mass. So dm by dt, that's the change in the mass of dye that's in the vat. Okay. Now, how does this mass change? Okay. Okay. Additional dye might flow into our vat, okay, and then some of it will flow out with the well-mixed solution, okay, dissolved in the water. Okay. So the change in mass is just how much mass is coming in minus how much mass is going out. Okay, well, how much mass is going in? Okay, well, pure water is being pumped into the vat because there was too much mass in there. It was too concentrated. So in fact, we can say there is no mass in. Okay. Now, how much mass is going out? Well, some of the mass that's dissolved in the water is flowing out. Okay. Now, we know that the solution is being pumped out at 16 liters per minute. If we know how much mass is in each liter, we'll be all set. Okay. So the amount of mass dissolved in each liter is the concentration currently in the vat. And we want to know how much is there, so we can multiply it by the 16 liters flowing out. And that's how the mass is changing. We're losing some mass as we go. So we'll have minus, now what's the concentration in the vat? Well, there's going to be 15 liters in the vat. Okay? It's 16 liters of water in, 16 liters of solution out. So the water level is not changing. Okay? It's not, if it was something like 20 liters in, then every minute we'd be gaining more and more and more water. Okay? We don't have that sort of situation. I mean, it's a perfectly good question, but that's not the one we're being asked about. So it's always going to be 50 liters at any time. Okay. So it's the mass in the vat divided by the volume in the vat. Okay, but that's, well, the mass in the vat, we have a function for that. 50 liters. Okay, it's minus because it was 0 minus. And how much are we flowing out? 16 liters per minute. And if we think about it, the liters will cancel out. And what have we got? Mass measured in kilograms per minute. Kilograms per minute. Well, that's mass over time. This makes sense as a setup. So, to clear things up, what's our differential equation? dm by dt is m, we could write m of t, over 50 times 16. Okay, this isn't a physics class, so we don't really need the units lying around. Okay. We could simplify that a little bit and say 8m over 25, or if you really want to, you could write 8/25 m of t. Okay. But there's our differential equation. Now it's up to us to try and solve it. And we could solve it lots of ways. Okay, you might be able, if you're very experienced, to figure out what m should be. Now, for example, I can already see when we derive it, we need to multiply by 8/25, but otherwise the function is unchanged. If I derive e to the t, it's unchanged. So if I add in a little constant here, that'll work. And any multiple of this will also work. So I know, just by inspection, that's the answer. But let's pretend we haven't done hundreds of mixing vat questions in our lives, because maybe you haven't. what do we actually do? Well, we could treat this as a separable differential equation. We've got our constant function, 8 over 25, and then m, our function in terms of m. Okay, we could rewrite this 1 over m dm, and bring the dt over to the other side. Okay. And now we can integrate. So we can get ln m. If you're worried about absolute values, try and convince yourself there's no way there can be negative mass in a vat. Okay, so you wouldn't need the absolute value. It would have to be positive no matter what. Yeah, but again, if you're worried about it, throw in the absolute value bars and see where that gets you. Let's see, we'll get 8/25 t plus some constant. Okay, raise both sides of the power e. Might choose to write that as 8/25 t times e to the c. Now we could say, well, e to the c, that's just a constant to a power of a constant. And what is that? That's a constant. And we could introduce a new constant d, if you really want to. Or you can, if you're very comfortable with what the constants are in differential equations, you can just have it be c still. Okay. But we'll go with d. We'll go with d just for fun. So our function must look like this, which is exactly what I predicted a little while ago. And exactly the sort of thing you can predict, too, if you do 100 mixing vat questions. Okay. So now, what do we do? Okay, well, we've got some information. For example, we know the vat begins, so that's time equals 0. Okay, we translate the English into equations and numbers and variables. We start with 20 kilograms, so we can use this information, the initial mass, to figure out our outstanding constant d. Okay, it'll be e to the 0, which is just 1, so d. d is 20. So our function is 20 e to the, I guess we could say 8t/25. Okay. That function models the mass that is currently dissolved in the solution that's in the vat, the 50 liters in the vat. And we didn't have to do anything with that. We didn't have to find another value. We just wanted to find a function. So there we go. 20e to the 8t/25.